In this video, I'm going to talk about shortest path algorithms that are Dijkstra algorithm and Bellman-Ford algorithm. So the problem is to find a shortest path from one of the vertex to all other vertices in a graph. There is a simple graph I have taken with just three vertices, T, U, and V. Suppose I select this as the starting vertex. Let us say T is my starting vertex. I have to find the shortest path from T to U and T to V. If I look into this graph, there is a direct path, means single edge path from T to U, that is of weight 5. But there is no direct path from U to T to V. So as there is no direct path, I say it is infinity. But we have to find out a path that may be of single edge or that may be having more than one edges. So from this graph we can see once I have reached U, T to U, and the cost is 5, from here I can see that there is a path to V and the cost of the path is 8. So this is what we do. So we have to find out the shortest path from some starting vertex to all the vertices, maybe a direct edge path or maybe going via other vertices. About a procedure, how to find the shortest path. For that, we look at a condition, that is a relaxation condition. So here I'll show you. Let us find the distance for each vertex. As this is our starting vertex, so distance for this vertex is 0. And from the starting vertex to U, the distance is 5. And from T to V, there is no direct edge. So I say this is infinity. So if I stop here, I can say that the shortest path from T to U is 5 and T to V is infinity. I can stop here. But no, if I follow the Dijkstra algorithm for finding the shortest path containing one edge or more than one edges also, so here I check this condition and try to update the vertices. If I say there is a shortest path from T to U that is of distance 5, and if I select this, once I select this, I see that from vertex U is there a shortest path to any other vertex. So I will check this condition, the distance of U plus cost of an edge U to V, that is 5 plus 3, that makes 8, and that is less than distance of V. Yes, this is infinity. So update this one, distance of V, make it as 8. So this vertex is relaxed after checking this condition. See how the Dijkstra algorithm works. If I make this as a starting vertex and the distance of this vertex is 0 and distance from P to Q is 1 and P to T is 7, P to S is 6, and P to R there is no direct edge, so let us make it infinity. P to U there is no direct edge, so let us make infinity. Now I have labeled all the vertices and found the distances from the starting vertex to that particular vertex. Now I have to find the shortest path to all the vertices. So here I start the procedure. I have to pick up the shortest path first. Means from P, which vertex is closest or very much closer to P. So that is Q. So I'll select this vertex. Once I have selected this vertex, I have to see that are there any vertices that are going to get relaxed. So yes, see this one. 1 plus 1, that is 2. So this is infinity. Now change. We got a shorter path from Q to R, that is 2. So the total path from P to Q and Q to R, the cost is 2. And next, here it is 1 plus 4, but right now it is labeled as 6. So 1 plus 4 is 5. So this is shorter than the existing path. Then from Q there are only 2 edges. Leave it. Now, as we have selected Q, now we have to select the next shortest path. So the remaining vertices for which we have the paths are 7, infinity, 5, and 2. So this is shortest one. So I'll select this one. This is the second vertex I'm selecting. From here, I'll see are there any vertices who are having shortest path via R. Yeah, 2 plus 1, that is 3. So this is infinity, change it to 3. And 2 plus 2, that is 4. So right now it is 5. So this 4 is smaller than that. So I'll take 4. So these are two vertices are updated. Yeah. Now how many vertices are remaining? T and U and S. 3 are remaining. 2 are already selected. We found the shortest path. Now I have to pick up the next smallest one. The next shortest path is U. That is, the distance is 3. So from here I should check, is there any update to other vertices? Is there any shorter path to other vertices from U? So from U there are no edges going out. So I'll just leave it. Now I have to find a shorter path, next one, that is, this is 4. So I'll select this one. This is the shortest one. Next 4 plus 3 is 7. This is already 7. So there is no change. So that's all. S is also selected. Now the only vertex that is remaining is T. So I select that one also. So the cost of the path is still 7. Right? So now here you can see that all the vertices are labeled with their shortest paths. So from P to Q it is 1, from P to R it is 2, so that is coming via Q. Then P to U is 3, that is coming via Q and R. And from P to S it is 4, it is coming via P, Q, R and then S. And from P to T it is 7 and it's a direct edge path. That's it. One more graph and let us find out the shortest path to all the vertices using the Dijkstra algorithm. And this is my starting vertex. I'm labeling the starting vertex. So this is 0, this is 1, 2, no direct edge path, no direct edge path. So it is infinity. Now I have to select the shortest path vertex, that is B. I select this one because it is 1, 2, infinity, infinity, infinity. So out of all these vertices, this is shortest one, which is having distance as 1. So I select this. From here I see, are there any relaxation to any vertices? B to C there is a edge, and 1 plus 1, 2, it's already 2, no change. B to D, 1 plus 3, that is 4, so change it to 4. B to E, 1 plus 2, that is 3, and it is infinity, change it to 3. That's it. From B there are 3 edges going out, so this is done. I have relaxed the vertices. Now select the next shortest one. So remaining are C, D, E, F. So shortest one is C. Select this one. So it means I have found the shortest path to C. Selecting means I have finalized the shortest path from A to C. That cost is 2. Now after finishing this, I see that is there any possibility of changing other vertices, the cost of other vertices. So let us see. So 2 plus 2, 4, and it is 3. There is no change. 2 plus 1 is 3, and this is 4. So change it to 3. That's all. There are only 2 edges going out from here. So this is updated. Finished. Now I have to select the shortest path from remaining. That is D, E, and F. These 3 are remaining. I have not found the shortest path to them. So I'll select the minimum one. So D and E, they are of same value. So I select D first. This is 3. And this is the shortest path to D. So from here I'll see, is there any relaxation? 3 plus 3 is 6. So this infinity, change it to 6. Then 3 plus 4 is 7. And this is already 3. So there is no change. That's all. Now remaining 2 vertices are there, E and F. E is the shortest one. So I select this. 3 plus 3 is 6. It is already 6. There is no update. Then last vertex remaining is F. So I have selected all the vertices. Selected means I have found the shortest path to them. And the shortest path starting from A to all other vertices is labeled above those vertices. That is B is 1, C is 2, D is 3, E is 3, and F is 6. If you want to analyze the time complexity of this algorithm for the extra shortest path algorithm, let us say there are V number of vertices, 1, 2, 3, 4, 5, 6. That is, size of V is 6. So number of vertices are V. So we have to find the shortest path to all these vertices from A to every other vertex. So let us say it is V. Then while finding shortest path to each vertex, we check, are the other vertices getting relaxed? So how many vertices we have to check? At most, we have to check v number of vertices every time. Let us assume this. So the time complexity will be v square. So if we say there are n vertices, then it will be n square. So it is order of n square, right? By using red black tree, it is said that the time complexity of this algorithm will be n log n, and how it will be using red black tree and how it will get this time, you can browse through and find out. Okay, next we move ahead. What will happen if there are negative edges in a graph? What the Dijkstra algorithm will do? So let me select this as a starting vertex. So this is 0 and this is 8, 2, this is infinity. Let us start. I'll find the shortest path to this vertex because this is minimum 2. So I'll select this vertex. First I'll select this vertex. So this is 2. Now from here I check, is there any shorter path to any other vertex? Yes, 2 to 3. So this is 5 and it is infinity. I'll modify it to 5. That's all. Now remaining vertices are 4 and 3. Out of this, this is 8 and this is 5. So I select 5. I'll select this vertex. Now let us see, is there any shortest path from here? 5 minus 6 is minus 1. So this is 8. Change it to minus 1. Now the remaining vertex is 4. So I select this vertex and its path is minus 1. That's it. So if there is a negative edge, it's working perfectly. Let us see what will happen in this graph. I'll use the Dijkstra algorithm to find the shortest path to all the vertices. This is my starting vertex. So the distance is 0, distance is 1, and this is 2, and there is no direct edge from 1 to 3, so this is infinity. Now I'll start selecting the vertices to find the shortest path. So the shortest one from 1, 2 and infinity is 1. So I select this one. So this vertex is selected. So it means I have found the shortest path from 1 to 4 is 1. It is finished. Now I select from here, there are no edges going out. So I select the next one. The next smallest one is 2 and the shortest path is 2. And from here I see that this can be relaxed. So I'll change it to 5. Now the next one remaining is this one. So I'll select this. And once I select this, I'll see that will the other vertices get relaxed. So 5 minus 6 is minus 1. So this will change to minus 1. So here Dijkstra goes wrong. The vertex which I already selected and said that the shortest path to this vertex is 1, later its distance is getting modified. Its path is getting modified. So it means in the first stage Dijkstra has given me wrong result. And as per Dijkstra, the vertices which are already selected, which you have already found the shortest path, you should not relax them. You should not update them as per the Dijkstra algorithm. So, but if I try to relax it, it is getting changed. So because Dijkstra says that once the vertex is selected and that is the only shortest path to that vertex, we don't have to update it further and it will not get updated at all. But in case of negative edges, it is getting updated, it is getting modified. So Dijkstra algorithm may not work perfectly always in case of negative edges. In the previous example where you saw there was a negative edge, this was negative edge, and here it was working, and in the other one it's not working. So it may or may not work when there are negative edges. Another algorithm, that is Bellman-Ford's algorithm. This algorithm is for finding the shortest path. Just now we saw that Dijkstra algorithm was unable to find the path perfectly always if there are negative edges. So it may work, it may not work perfectly. So here we have another algorithm which works always when there are negative edges, but though it is also having its drawback. So first let us see, it can find out the shortest path in this case. So what Bellman-Ford says that In contrast to Dijkstra, where Dijkstra was saying that relax the vertices only once, but Bellman-Ford says that go on relaxing the vertices for some number of times so that finally we get the perfect shortest path or correct shortest path to all the vertices. So let us see what he says. I am going to show you the procedure of Bellman-Ford. So he says that from the graph you make the edges, list of edges. So here I pick up the list of edges. So I will pick up D to B, the last one. I'm selecting this one first. Then next is C to D, and next is A to C. The next one is A to B. Right? These are the list of edges. So I have only 4 edges. So I have taken a very simple graph to understand this. So I have not started from A to B. I have started from D to B. You can realize why I did so. So let us follow the procedure what Bellman-Ford says. First step is take the list of all edges and mark the distances for all the vertices. So this is 0 and make all these as infinity. Even there is a direct edge path available, but don't consider it, mark it as infinity only. So the starting vertex, that is the source vertex, mark it as 0, rest of the vertices as infinity. That's it. Now go on relaxing the edges. For how many times? Number of vertices are 4. So do it for number of vertices minus 1 times, that is 3 times. Go on relaxing them. Let us do it. D to B. D is infinity. So infinity minus 6 is infinity only. And this is already infinity. So there is no change. Then C to D. Infinity plus 3 is infinity only. And this is not less than or infinity. So this is infinity only. A to C. A to C. 0 plus 2. 0 plus 2. This is 0 and 2. 0 plus 2 is 2. This is infinity. So change it to 2. 2 is smaller than infinity. Then A to B, 0 plus 1, 1. So this is infinity. 1 is smaller than infinity. Change it to 1. So this I have done it one time. So I will maintain the count. So I have finished it for one time. Now let me repeat once more. D to B. D is infinity to B. Infinity minus 6 is infinity and that is 1. So it will not change. C to D. 2 plus 3 is 5. Right? So this will change to 5. Then A to C. 0 plus 2 is 2 and it's already 2. A to B. 0 plus 1 and 1, it is already 1. So I have done it for 2 times. So 1 plus 1, 2 times. Now let me repeat one more time. D to B. 5 minus 6 is minus 1 and this is already 1. Change it to minus 1. Then C to D. 2 plus 3, 5. It's already 5. A to C. 0 plus 2. It's already 2. A to B. 0 plus 1. And 1, this is minus 1. So 1 is not less than minus 1. So no change. So that's it. I have finished it for third time. So I have completed the relaxation of all the list of edges 3 times because there are 4 vertices. I have to do it for 3 times. So the idea behind Bellman-Ford is go on repeatedly relaxing the vertices for v minus 1 times and all the vertices will definitely get relaxed and finally you get the correct shortest path to all the vertices even in case of negative edges. Right. How much time Bellman-Ford algorithm takes? As there are e number of edges and we have to go through all of them for how many times? V minus 1 times. V minus 1 times. So this is E into V. V is N. So this is almost N square. Right. V is the edges. Just we are relaxing all the edges one by one. So E number of edges. And how many times we are doing it? Number of vertices minus 1. Number of vertices, let us say n. So E into n. So if we say both are n, so it is order of n square. And sometime if there is a complete graph, let us say the graph is like this. If there is a complete graph, in a complete graph we know that the number of edges will be equal to n into n minus 1 by 2. So this will be n square edges. So then the time complexity will be E into n, and E itself is n square. So n square into n will be n cube. So the time complexity of Bellman-Ford in case of complete graph, will be order of n cube. Now let us see what will happen in this graph. I have just added one more edge here with the cost as 1. So it's just same as previous graph, but just a new edge is added. So I'll perform Bellman-Ford on this one. I'll take the list of edges D to B and C to D, A to C, A to B, and B to C. So let me go on relaxing all of them. So first I label the vertices. This is 0 and this is infinity. So to all of the vertices we should make it infinity. Let us relax. D to B, infinity minus 6, infinity, no change. C to D, C to D, infinity plus 3, infinity, no change. AC, 0 plus 2, that is infinity here, so it will change. This is smaller. A to B, 0 plus 1, 1, so this will change to 1. Then B to C, 1 plus 1 is 2, and it's already 2, no change. Now relax again. D to B, infinity minus 6, there is no change. C to D, 2 plus 3, 5, so this will change to 5. A to C, no change. A to B, there is no change. And B to C, B is 1, 1 plus 1 is 2, then it will remain 2 only. So I have finished 2 times so far. Third time, D to B, 5 minus 1, sorry, 5 minus 6 is minus 1. So this will change to minus 1. Then C to D, 2 plus 3, 5 as it is. A to C, 0 plus 2, that is 2 only. A to B, 0 plus 1, and it's already minus 1, which is smaller, so no change. B to C, minus 1 and 1 is a 0, and this is 2, so this will change to 0. I have finished for 3 times, but I relax one more time and see what will happen, as Bellman was saying that if there are 4 vertices, you relax all of them for 3 times. Every vertex will have a shortest path and it will be a correct shortest path. That's what Bellman-Ford was saying. Let us try it again once more. Let us relax all of them. D to B, 5 minus 6, it's minus 1 only, right? Then C to D, 0 plus 3 is 3 and it is not 5. So change it to 3. 5 was greater. So 3 is smaller. A to C, 0 plus 2, 2 only. A to B, it is 1. It is minus 1 already, is better. Then B to C, it's minus 1 and 1, that is 0. No change. So you can see that after finishing it for 3 times, I got one of the vertex relaxed. That was 5 and it became 3. So there is a change. If I repeat once again, definitely I'll find some more vertices get relaxed. Let me do it again. B to D to B. So 3 minus 6 is minus 3. So this will be minus 3. Minus 3 is smaller than minus 1. C to D, 0 plus 3 is 3. That's as it is. A to C, that is as it is. A to B, as it is. B to C, minus 3 and 1 is minus 2. This is also getting relaxed. 2 vertices are getting. So it means if I go on checking the condition of all these list of vertices, the vertices may be changing their distances again and again. So what's the problem here with Bellman-Ford? So the problem here is, if you see this B and D and C, there is an edge with 1, there is an edge with 3, there is an edge with 6, and these three are forming a cycle. And the cost of the cycle is 1 plus 3 minus 6 is minus 3. So the total cost of a cycle is negative. So this means that if there is a negative edge, no problem with Bellman-Ford. But if the edges in the part of a cycle and the total weight of a cycle is negative, then Bellman-Ford also cannot work on that graph. So Bellman-Ford fails if there is a negative cycle in the graph. So here is a negative cycle, right? So this is the negative cycle in the graph. So Bellman-Ford doesn't work. But after relaxing the vertices for edges for 1 minus 1 time, n minus 1 time, and again if we repeat it for one more time, Bellman-Ford can show that there are some vertices getting updated. It means there is a negative cycle. So Bellman-Ford can detect if there is a negative cycle, but it cannot solve if there is a negative cycle. So hope you have understood both the algorithm and able to compare them. Right? Thank you for watching. Please leave your feedback.